Hello, my name is Todd Evans and I am a Level 2 Product Support Engineer at Cole Morgan. And this video series is an introduction to the AKD Ethernet IP servo drive. Welcome to video 8 of the AKD Ethernet IP video series. In this video, we will cover the AKD Drive add-on instruction and command and response assemblies. Cyclic data exchange between the PLC and the AKD Ethernet IP drive is accomplished with the command and response assemblies, and they consist of 64 bytes of output data, the command assembly, and 64 bytes of input data, the response assembly. This training section will go into detail how the information is exchanged between the PLC and the drive. We will also describe how the data is transferred between the generic Ethernet module that is the AKD drive and the ladder and add-on instructions. If you look at the screenshot below, you'll note that when the generic Ethernet module is declared along with the IP address for that access, there are 64 bytes of input and 64 bytes of output under the connection parameters. If you look at the connection parameters, there's input, output, and configuration, and for each there is assembly instances and sizes declared for each. This definition and details are covered in the AKD Ethernet IP communication manual. Also notable is that the generic Ethernet module gets a name, in this case AKD_1, that the COM format is data short integer, and the IP address for the target AKD Ethernet IP drive. Once configured, tags will be added to the controller tags using the name of the generic Ethernet module entered in the name field under the general tab of the generic Ethernet module setup, AKD_1 in this case. You noticed in the screenshot of the controller tags that there are 3 entries for the AKD_1. That is :C, I, and O, and this corresponds to the connection parameters of configuration, input, and output. In the AKD Ethernet IP communication manual, there are tables that describe the assemblies. What is shown here is the command assembly, and you recall there are 64 bytes of output, and here it describes each of the bytes from 0 to 63 for 64 total. Likewise, the same can be said for the response assembly as well. In the simple example project, the AKD drive add-on instruction is tied unconditionally to the left rail in rung 0, so the add-on instruction is evaluated with every scan. The AKD drive add-on instruction entries are as follows. The AKD_drive field was declared with the same instance name as the generic Ethernet module, just for consistency. This isn't required, but may be easier to correlate which AKD drive block is associated with which generic Ethernet module and IP address. The access_input and access_output entries must point to the controller tags of the input and output assemblies of the generic Ethernet module that were created when the generic Ethernet module was configured and declared. The access_internal will be a tag with a tag name that will be used to identify the access with all other add-on instructions that will point to that access, and thus the AKD drive. To summarize the connections, if you look at the screenshot below, the green arrow is the generic Ethernet module name and points under controller organizer Ethernet and for that particular generic Ethernet module. The yellow is the connection parameters, and you can see those entries in the tag database. The purple is the AKD_drive add-on instruction instance name. The red is the input of the connection parameters. The blue is the output of the connection parameters, and black is the axis underscore internal name, and in this sample project was called axis underscore 1. The tag name of the axis internal for that axis entered into the AKD Drive add-on instruction is used later in the ladder for diagnostics, and also for the axis field entry of all add-on instructions that will be codependent on the AKD Drive add-on instruction for that axis. Essentially, the AKD Drive add-on instruction acts as a liaison between the generic Ethernet module communications and all the add-on instructions for that axis. Because of this, the AKD Drive add-on instructions should be evaluated before the AOIs that depend on it in the scan. Otherwise, erratic behavior and timing may occur over Ethernet IP. So in the example below, we show that the axis internal name is axis underscore 1. It's unconditionally tied to the rail and at the top of the ladder. Then in the next rung, we show one of the status attributes, which in this case tells you if the drive is enabled or not. And we utilize that for a coil in the ladder logic itself is the axis enabled. But you'll notice that the convention is the name of the axis dot status dot enable. Also, another example is the next run, which shows the AKD enable add-on instruction. You'll notice that that add-on instruction requires an axis entry. In this case, we want the AKD enable to enable the drive that is called axis underscore 1, and so therefore you have to enter that name into the add-on instruction or any other add-on instruction that you plan on using that's correlated to axis underscore 1. The key to understanding how the AKD Drive add-on instruction acts as a liaison between the generic Ethernet module and the codependent add-on instructions for that axis is to understand the axis internal structure that is created once you add a tag for the axis internal entry of the given AKD Drive add-on instruction. In the sample project, the axis internal name was called axis underscore 1, and when that tag is expanded, a structure that was created for the tag is shown. You'll notice below, when expanded under axis underscore 1, the structure includes control, status, input, output, response message type, command timeout, current position feedback, and current velocity feedback. Under the axis internal name dot control, when expanded, the control word functions bits are shown. This corresponds to the control word as defined in the AKD Ethernet IP communications manual. Under the axis internal name dot status, when expanded, the status bits are shown. This corresponds to the two status words defined in the AKD Ethernet IP communications manual. Under the axis internal name dot input, when expanded, displays bytes 0 through 63 for a total of 64 bytes. Under the axis internal name dot output, when expanded, displays bytes 0 through 63 for a total of 64 bytes of output data. The AKD Drive add-on instruction passes the axis internal dot control bits to the axis internal output tags in the structure, and then also copies all 64 bytes of the axis internal name dot output to the command assembly of the generic Ethernet module. Additionally, under the axis internal structure in the controller tags, there are several additional entries: response message type, command timeout, position feedback, and velocity feedback. Behind the scenes, the following slides will detail step by step how the AKD Drive add-on instruction works behind the scenes. In step 1, the AKD Drive add-on instruction copies the 64 bytes of input data, that is the response assembly, from the generic Ethernet module, which, if you look down below, was declared as AKD_1:I in this case, to the access internal.input.data, access_1.input in this case. If you look down below, the flow diagram shows step 1, input data response assembly from generic Ethernet module. The AKD Drive copies and sends it to the access_internal.input.data. Also, there are snapshots below that show the declarations from the controller tags. Keep in mind, during execution, the codependent add-on instructions depend on the access_internal.input data during execution. In step 2, the AKD Drive add-on instruction sets the status bits in the structure access_internal.status based on the current values of the access_internal.input.data that were copied in step 1. Again, looking at the flow diagram, you can see that the access_internal.input.data is taken, and then the AKD Drive sets, based on those values, the bits in access_internal.status. And again, the snapshots from the controller tag database is shown below. In step 3, the AKD Drive takes byte 3 of the input data that was copied in step 1 and performs an ANDing function on it with the hex 1F to mask it for response errors. The result is copied into the access.internal structure entry access.internal.response message type. If you look at the snapshots from the controller tag database, the source and destination are demonstrated below. In step 4, the AKD Drive takes bytes 8 through 11 of the input data that was copied in step 1 to the access internal structures entry access_internal.feedback position. Again, the flow diagram is shown to demonstrate the copy, and there are screenshots from the controller tag database below. In step 5, the AKD Drive takes bytes 12 through 15 of the input data that was copied in step 1 to the access internal structures entry access_internal.velocity feedback. And again, the flow chart and the snapshots from the controller tag database demonstrates the copy and the source and destination. In step 6, the AKD Drive takes the access internal.control bits that make up the functions of the control word bits 0 through 7 and sets the corresponding bits in byte 0 of the access_internal.output entry of the structure. If you look below, there's a flow chart that shows the AKD Drive setting the bits, source and destination. And you'll also see the snapshot from the controller tag database. You'll see that the access_1.control from the sample project has the bits of the control word, and that gets set to the access_1.output.data bytes 0 in bits 0 through 7. In In step 7, the AKD drive takes the access internal output data, all 64 bytes, and copies it to the 64 bytes of the communication parameter command assembly for output of the generic Ethernet module AKD_1:0 in this case. Keep in mind the codependent add-on instructions write to the access_internal.output data during execution. So step 7 is where the data gets sent written out to the drive via the generic Ethernet module. And again, below a flow diagram and the snapshots from the controller tag database indicates the copy that the AKD drive add-on instruction performs. Handshake. The following diagram demonstrates the handshake using the AKD move add-on instruction as an example. In the normal Ethernet IP application, the motion task 0 data is transferred from one variable to another 6 times before the answer arrives back at the move block, 4 times inside the PLC and 2 times outside the PLC. If you look at the flow diagram below, it shows that the access internal variables go from the move block, get updated into the AKD drive block. That becomes the output through the generic Ethernet module into the drive. Then it's routed out of the drive through the generic Ethernet module, becomes the input or read data. It gets updated into the AKD drive communication block, and then that information then is routed to the AKD move block. This can happen multiple times as long as the AKD move block in this example continues to execute. The add-on instructions use the methods defined in the AKD Ethernet IP communication manual. In fact, it is possible to use these methods without the use of add-on instructions at all. However, the add-on instructions automate each method and is more convenient to implement since the code is already embedded inside the add-on instructions versus writing the code from scratch and for every access. From the AKD Ethernet IP communication manual, there are command types such as hex 6 is a position move and hex 7 is a jog move, etc. There are also various methods listed in the table of contents shown below, such as homing, running a stored motion task sequence, etc. Although we've created add-on instructions that can perform these command types and methods, it is helpful to understand what is happening behind the scenes. Here's an example of setting up a command type hex 06 position move. Below you'll notice that byte 2 is the command type, in this case hex 06, and then bytes 8 through 11, the position data is populated. Bytes 12 through 15, the velocity data is populated, and so forth for accel and decel. This is what the AKD move add-on instruction essentially does, and then it starts to move with the control word load start bit 0 and byte 0, the command assembly. I've color coded the specific bytes related to each entry. You'll see there's labels, command type, position, velocity, accel, decel. The important point is that each add-on instruction uses different methods, and they all use the same 0 to 32 bytes, which is called a static map. More on that later, of the command and response assemblies. This is the reason that only one add-on instruction can execute at a time for access. To send one command type while another is executing is to overwrite the static map data shown in green below and the command type in byte 2 with new information. This can cause timing and communication issues. To hit home some of the things that we've talked about, I've got my PLC project online with the PLC in RSLogix 5000. I can right click, open instruction logic at the AKD Drive, add-on instruction. You actually can study it and see internally what it's doing and how it operates. You'll notice that many of the tags inside the AKD Drive add-on instruction point to the structure axis_internal. If you go to the controller tags, this was called axis_1. I can expand. One of the things that I can look at, for example, as the scan takes place and the AKD Drive add-on instruction updates the structure, I can click on status, for example, and I can see currently some of the status bits, the states in the status words of the response assembly. For example, home level, I can see it's a 1, which means that the drive is homed, the drive is enabled, and things like that. You can also see in the control word, I had already executed the AKD enable add-on instruction. If I want to disable it, for example, I could come down here, disable, go back to controller tags, look at the control group of the structure, 0, not enabled. I can go back to status and look at enable and it's off, things like that. I'm going to re-enable it. Since I'm already homed, I'm in position mode, I'm going to jog the axis forward and you can go and you can go back to the structure. You can see that my positional value is changing. You can see that I have velocity feedback. One of the things that you can also do is, if you look at the output data, if I go to binary and I look here, there's a command type 7, which you'll recall is a jog, so that makes sense. You can look and see how the add-on instruction populates other data within the command assembly. So likewise, you can look at the input data. I've also used this to troubleshoot in some cases where there's a problem with one of the add-on instructions producing an error, and I have looked here at the load start bit and it was continuously going on and off with every scan, and in that case that was because there was an add-on instruction that was always executing every scan, and that was causing a conflict with the other add-on instruction. So these are some of the things that you can look at within your controller tags and correlate it to what's going on in your ladder as well.